We're now going to learn about lateral static trim and stability. In the previous section, we learned about longitudinal static trim and stability, and we assumed that the aircraft was symmetric about, so if this is the x-axis coming out the nose of the aircraft, y is out the right wing, and z is down, we assumed that the aircraft was symmetric about the xz plane here. And so we looked at forces in the x direction, forces in the z direction, and moments about the y-axis, or the pitching moment of the aircraft. And we could study that in somewhat two-dimensional flow, two-dimensional motion, meaning that it could pitch and also trim in x and z. And today we're now going to shift our focus to the lateral forces and moments on an aircraft, and we're going to look at that from a top-down view here. So if this is the wing of an airplane, and we've got a fuselage here and a horizontal tail, then of course X is out the front of the aircraft, Y is out the right wing, and then Z would be into the page here. So now let's just label the forces and moments on this. So the pitching moment that we've discussed before was the moment about the y-axis, and we gave that the symbol little m. We are now going to also look at a moment about the x-axis. So a moment about that axis we'll call little l, that's the roll axis. And then we're also going to look at a moment about the z-axis, which we're going to call n, or ya. Okay, now each of these moments follows the right-hand rule. So if you put your thumb in the direction of that axis, then your fingers curl on your right hand, your fingers curl in the direction of a positive moment. So a positive rolling moment, for example, is when the right wing would drop. Then the aircraft would experience a right roll. Positive yawing moment means that the aircraft would yaw the nose to the right, and then a positive pitching moment is a nose up pitching moment, which we discussed over here in the when we discussed the longitudinal forces and moments. Okay, so we also need to add two new angles. So we're familiar with the angle of attack, and that's the angle that the x-axis makes with the free stream. Remember, so if we so over here, if we have some free stream velocity coming in v infinity, alpha was the angle of attack relative to the x-axis. Well, now we're going to have another angle called beta, and that's an angle here. This angle here, if the free stream is coming in with some side slip, we call that a side slip angle. If it's coming in with some component in the y direction, okay, so it's not just solely in the xz plane. If we have some component now coming in from the side, we're going to call that angle beta. That's a side slip angle. So alpha and beta are aerodynamic angles. So I'm just going to write that down here. Alpha and beta are what we call aerodynamic angles, because they tell us the orientation of the aircraft relative to the direction that it's moving, or the direction of the free stream velocity, okay? And our aerodynamic forces depend on those two aerodynamic angles. Now there's another angle, a lateral angle, that we need to discuss. And so if I'm looking from the back of the aircraft and my wings are slanted relative to the horizontal, so this is the horizon, and our weight vector would be straight towards the ground. So this is what we call a bank angle, okay? And actually, because the wings might have some dihedral in them, we're going to measure this bank angle relative to the XZ plane of the aircraft. So that's the plane of symmetry of the aircraft. And this is what we're going to call phi, the bank angle. So it's the angle that that xz plane makes with the gravity vector, which is pointing straight down. So the angle between these two is called phi. Now phi is a lateral angle. So all three of these are important angles, alpha and beta being aerodynamic angles, but phi is actually an orientation angle. So it tells us about the orientation of the aircraft relative to the ground, but it turns out that none of the aerodynamic forces or moments on the aircraft depend on our bank angle. The aerodynamic forces and moments depend only on how the aircraft is moving relative to the free stream velocity, which is defined by these two angles here, alpha and beta. Our bank angle simply tells us what direction the weight vector is pointed in relative to the aircraft. And so that's obviously another force on the aircraft, and we use that weight vector. We have to account for that weight vector when we're trimming the aircraft. But that's not an aerodynamic force, okay? That's a body force due to gravity. And so our aerodynamic forces depend only on the aerodynamic angles. This angle is inherently different, although still important, and we're going to see why here in a minute, or in the coming lectures. This is a very important angle here, but our aerodynamic forces are independent of this, but our weight vector does depend on it. Okay, so our body force does depend on phi, and that just tells us the orientation of the aircraft relative to the horizontal or relative to the ground. Okay, so let's just quickly mention our little alphabetic triads again that we're using here. So x, y, and z are our axes, and a moment about the x-axis we use L, a moment about the y-axis we use M, a moment about the z-axis we use N. So those are moments, and then eventually we're also going to talk about velocities and rates. So velocities along each of these axes we call u, v, and w. So those are components of v infinity divided into the xyz components relative to the aircraft. And then rates, as we rotate about each of these axes, we're going to call those p, q, and r. Those are rotation rates about the axes. Okay, so we're going to be focused a lot on these moments here in this particular section of static trim and stability. We're going to be talking a lot about those, and also we're going to be talking about the force in the y direction. Okay, so before we talked about the force in the x and z directions, fx and fz, and now we're going to also be talking about this lateral force in the y direction, f sub y. Okay, so let's talk about how we non-dimensionalize each of those. So for example, the rolling moment, L, we're going to non-dimensionalize that by 1/2 rho v infinity squared SW BW. Okay, so this is a moment, so we use the dynamic pressure here times an area, and that gives it a force, and then we need a length multiplied by that, and we use the wingspan actually to non-dimensionalize this lateral moment. Now remember, to non-dimensionalize the pitching moment, we use the mean chord of the main wing. That's what's traditionally done. But to non-dimensionalize a lateral moment, L or N, we're actually going to use the wingspan here to non-dimensionalize that. And we'll call that the rolling moment coefficient. So we'll do that for the yawing moment coefficient, just the same. So we've got 1/2 rho v infinity squared SW times the wingspan. And then we're also going to have a coefficient of force in the y direction. We'll call that C sub y. And that would be the y force divided by 1/2 rho v infinity squared SW. Now this doesn't need a length because it's not a moment, it's a force. And the dynamic pressure times an area is a force. And so that's everything we need to non-dimensionalize that force. Okay, so these are coefficients that we'll be using throughout this section to look at the rolling and yawing moments and a side force. And one last note about one difference between lateral and longitudinal is that previously, if we were just studying things in the XZ plane here, forces and moments, and so the aircraft would move in that XZ plane. If you have a perfectly symmetric aircraft about the XZ plane, okay, so if our aircraft is perfectly symmetric left to right, and we have only longitudinal disturbances, that does not necessarily produce any lateral motion, okay? That aircraft can stay, the motion of that aircraft can stay in the XZ plane if we have if we have a perfectly symmetric aircraft and only longitudinal disturbances or forces and moments. What's different about the lateral is that that lateral forces and moments actually end up also producing longitudinal motion. Okay, so lateral motion is inherently three-dimensional. We can't look at this in a two-dimensional plane like we could for the longitudinal stuff over here. We inherently have to think about this aircraft in 3D because any lateral disturbance or force or moment can also excite longitudinal motion. Okay, so that's one difference about the longitudinal and lateral. And just as a final thing here, I'll just kind of box this off. This was about our longitudinal discussion, and then the rest here is more focused on the lateral discussion that we'll be covering in the next few lectures. One thing I forgot to point out that is worth mentioning before we go on to the next section is that a positive beta is when velocity is coming in from the right side of the aircraft. And so a pilot will call this wind in the right ear, meaning that velocity is coming in from the right-hand side. Now, this is actually similar to how alpha is defined, where alpha is a positive alpha is when we have velocity coming in from the z direction. So we have so the z points out the bottom of the aircraft. If we have velocity coming in from that side of the aircraft, that's positive alpha. If we have velocity coming in from the right side of the aircraft, which is positive y, that's positive beta. Okay, so I've drawn this in a positive direction here, and that's just one way you can remember which way is positive for beta.